Hello and welcome everyone to this Monitoring Coastal Erosion from Space workshop. My name is Laure and I am the EO technical lead for the Coastal Erosion project. We're now going to present you our processor that have been developed within the Coastal Erosion project. The first one is the co-registration. So all images that we use for the project have been co-registered. It's a very important first step. So why we need a co-registration? So have you seen with Martin with the limitation of the satellite acquisition, between two satellite acquisition of the same area, we can sometimes observe a shift. And for example, for Sentinel-2, this shift can reach 12 meters. The co-registration is a process which aims to improve the positional accuracy between two acquisitions. We will have a master image acting as a reference, and a slave image, which will be modified to perfectly overlap the master one. The co-registration is generally used to calibrate image from the same sensor at the same resolution. The co-registration is a really important first step, especially when we're working with time series. Because, for example, if we're working in change detection, we want to be sure that the change we observe is not due to an image misplacement, but really because we had a morphological change at the coast. So the co-registration is evaluated thanks to a similarity score. So this one, the SSIM, is the structural similarity index. So now we have two examples of the Sentinel-2 image before and after the co-registration. We focus on one little pixel, so you can see on the zoom. And before and after the co-registration, we can observe a shift around 10 meters to the top. On one image, we can observe similar change. So if it's 10 meters to the top, we will have the same change for other pixels. So here, the same image, but instead of focus on one pixel, we're focusing on a group of pixels, and we have the same range of change, 10 meters to the top. So how we co-registrate? The co-registration starts with the inputs. Which image can be used in inputs? So for example, for the master image, we have to meet some requirements. You have to be cloud-free, no glint. We have to see the whole image. So here in the image of 2018, it's totally cloud-free, no glint. This image can be perfect for a master image or for a slave image. On the other hand, for 2016, here this image cannot be used as a master due to the cloud that we can observe in the north part of the image. So the co-registration is evaluated thanks to the SSIM score. So here we have before and after. So we can see that before the co-registration, we had some value around this average of 0.5. But after the co-registration, most of our value are in this green rectangle, which is between 0.75 and 1. So for the co-registration, we need a very good quality of input, especially for the master image, cloud-free. We have to see the whole image. And in our result, we saw that we'll be able to reach 3-meter accuracy in some areas. Thank you. And now we're going to pass for the presentation of shoreline and waterlines.
Hello, I'm Scott Miles from ARGANS, and I'm going to be presenting to you about the waterlines, shorelines, and SAR products. If you have any questions at any point, you can ask them in the app. Okay, so what is a waterline? So the waterline is the instantaneous boundary between the land and the sea. To capture this boundary, we harness data captured from multispectral imagery. And we know that different types of land cover and water give different information and signals. And we can use this to identify different areas within the image. So the waterlines are identifiable in the images where the image characteristics change sharply when moving from land to sea. And the images capture the instantaneous waterline as the satellite passes. So therefore we capture the variability in the tidal regime and the sea state. So the waterlines are useful as they help us help reveal the coastal geomorphology. So we can use this to monitor geomorphological change. This is an example from Canada, where we see quite drastic changes to a headland over a few years on this bit here. And we have 25 years of satellite data, so Landsat 5, Landsat 8, and Sentinel-2 to help us observe these changes. Okay, so to detect the water lines, we use band ratios. And what this is the ratio between a color band and the near infrared band from the bands within the sensors. So using a ratio helps us to extract the waterline more easily than just using, for example, the color bands. And using the different bands, we can test different colors. So for example, on the image on the right, we can see that when we use a green color band and a near infrared band, we get a lot of noise out to sea. And when we use a blue band and the near infrared band, we lose this noise and we get a very clean waterline. So each area needs some testing, as every area that we look at is slightly different and will give different results. So with this band ratio, on the land, we have very sharp, very high value reflectance ratio values, and to sea, we have very low reflectance ratio values. And what we're looking for is this threshold value directly in the middle. So this image on the left is basically showing you we'll use a value of about minus 0.2 as our threshold, and then this indicates where the waterline will be on the image. So we use a moving window approach. So we move across the coastline and take 75 by 75 pixel areas, which are then analyzed to find an ideal threshold value. So challenges to the optical waterline include cloud cover, sediment, and large tidal regimes, often around estuaries, for example, where the water is more turbid and suspended sediment can create artifacts on the images. So the processor has some built-in internal quality control, and every waterline we produce has a associated quality control score that looks at the intrinsic properties of each line. So this image on the left is showing the artifacts out to sea, which have been highlighted as having very low confidence that this gives a true representation of the waterline. So the score for each segment of the line is between 0 and 100, where 0 is very low confidence and 100 is very high confidence. We can also use a heat map approach or a density map to compare the waterlines against each other. So if we have a lot of waterlines in a very similar area, we can say that it's likely that this is likely to be a true representation of the waterline, and anything further away out to sea, for example, is given a very low QC score. So for Ireland, we've looked at 4 sites, and each one has given us a large number of waterlines over a quite extensive area. The outputs are Esri shapefiles, and each comes with a built-in quality control and accompanying metadata. Okay, so yeah, this presentation is about the transformation from waterline to shoreline. So the waterline indicates the land-sea boundary at an instant moment in time, and this could be anywhere in the intertidal area or the swash zone. It all depends on the tides, the waves, and even the air pressure. So for measuring coastal change, this constant variability isn't helpful, and changes to the coastal environment are rarely obvious. So to remove this variability and to detect meaningful change, we transform the waterlines into shorelines. So through this transformation, we calculate where the waterline would be positioned if we change the water level to a fixed value. So by normalizing the waterlines to a fixed reference point, areas of accretion and erosion become easily detectable. So to transform the waterline to shoreline accurately, a wide range of auxiliary data is needed, including the tide, the wave, beach profiles, and datum measurements. So ideally, this data should come from measurements, as using model data can often lead to significant uncertainties. Using this data, we calculate all the components of the instant water level. So this is shown in the right image, such as the wave run up, the tide, and water level anomalies. And with this new accurate waterline elevation and using the in situ slope data, we can now calculate the shoreline position using geometric equations. So this figure shows how the water lines with their variable water level can be corrected to the same datum height. It's most common to use tidal datums as the fixed reference. And what these are average or extreme values of the tidal cycles, such as the mean sea level or the highest astronomical tide. As well as coastal research, these datums are also helpful for nautical cartographers and even provide a reference for defining legal spatial boundaries. So here is an example of some datum-based shorelines. The image to the far left shows a single waterline that's been transformed into many different datums. This image in the center is showing you when we transform many waterlines to the same datum. And the image on the right is showing an example from Wexford in Ireland, where we can see how the single waterline can be transformed into many different shoreline datum. So as you move along a coastline, the tidal height and the tidal range are going to change. So in some coastal locations, this can change drastically over just a few tens of kilometers. So for example, Wexford in Ireland has quite a complex tidal regime, and this is one of the areas where using a single measurement for the tide can be quite problematic. So to account for this, the Shoreline Processor uses multiple tide gauges and datum information, and then interpolates values based upon the distances between the two. So this novel approach allows for the Shoreline Processor to create shorelines across hundreds of kilometers of coastline without losing any accuracy due to changing tidal dynamics. So using a wide range of auxiliary data allows for consistent, accurate shorelines. However, using multiple sources of data comes with a significant cost. So first, sourcing data with the same temporal range is quite challenging. And this means that only the dates where all the data is available is it possible to construct the shorelines. Secondly, a lot of the data is difficult to source, especially if it doesn't already exist. So this example on the right is from Canada, where we can compare the waterline extent in purple to the shoreline extent. In certain areas, it's quite difficult to find this data, and then this can seriously limit the extent of the shoreline. So each of the auxiliary data sources we use, the waves, the water level, all have an inherent uncertainty in their measurement. So this uncertainty varies depending on the type of data being used. So as you can see in the figures above, the measurements and uncertainties can vary massively depending on what type of data you're using. So when we use multiple sources of model data, so if we use a lot of low resolution data, this can compound the uncertainties and lead to very high uncertainty in the final shoreline product. So by using high quality auxiliary data, the uncertainties are controlled, the shorelines are more accurate, and it becomes easier to distinguish shoreline change. So although the production has shown good results, there are still some challenges when it comes to creating shorelines. So one of the main challenges, for example, in an area around Dublin, is changing intertidal area, or especially around mud flats and sand spits. So a low tide waterline converted to a shoreline will not be able to match the orientation of the coast at high tide. This is a showcase of the SAR products, originally by Albert, but presented by me. So the initial plan of the project was to focus the production on the waterline retrieval, where the processor is able to generate a waterline for every SAR image. However, after consultation with end users, we found the coastal community was also interested in the analysis of the change in the topography of the coastal area, not only in the dry part, but also in the bathymetry. So we started the development of these two new processors, which are currently being assessed over some specific areas. However, these are still in the prototype stage. So the terrain elevation processor and the bathymetry processor. So one of the main advantages of SAR is the ability to penetrate cloud cover. And this is especially useful in mid-latitude regions where cloud cover can be quite extensive. This gives SAR the ability to substitute optical products when the cloud cover is too high. Furthermore, as the SAR sensor doesn't need sunlight, it is possible to take a snapshot at any point during the day or night. And this allows for high frequency coverage of the target area. So although the SAR products have some major advantages over their optical counterparts, there are still inherent limitations, especially in coastal zones. So for example, during high wave conditions, the surface roughness of the ocean increases and the backscatter being received by the sensor also increases. So this creates less contrast between the land and the sea, and it makes identifying coastal features more difficult, such as sandbanks around Wexford Harbour that you can see in the image above, with the left image showing the SAR image and the right image showing the optical Sentinel-2 image. So here you can see on the left image the same location, but in low wave conditions. And the coastal features here are much more easy to identify around Wexford Harbour. Another limitation is the effect of the topography. As the satellite is viewing the coast from an angle rather than from directly above, if there's any high cliffs in the area, this can cause error when calculating the position of the waterlines. So the Waterline processor has two main steps. The first one is in charge of retrieving the line between the water and the land for each input image. Image processing techniques such as segmentation and noise reduction are applied in this first step. The second step is in charge of estimating quality parameters that will allow us to classify the lines in order to eliminate outliers from the final product. It's based on two parameters, the distance to a reference line and the density. So by estimating the quality parameters, it's possible to separate the good lines from the erroneous lines. And this can be seen from an example in Canada with all the processed water lines overlaid on top of each other, with the green areas indicating the good lines and the white ones indicating the bad lines. So by using a comparison of these water lines against a reference shoreline, it's also possible to track trends in the waterline position changing over time. So this is an example in Tordera, where in Spain, where we see quite large erosion trends. And using the waterlines here, we've been able to estimate a change of about 7.85 meters per year. Okay, that's all from me. Thank you very much. If you have any questions, you can answer them in the app and we'll get back to you as soon as possible. Thank you.
We're now going to present you the Backshore Classification processor. So as you've seen with Scott, sometimes the shoreline is at the wrong position depending on the feature we have on the coast. So we try to identify the different coastal areas. So for example, here, behind this red line, we have some man-made features, for example, harbor, city, we can also find crops. Then between the red and the green line, we'll find this buffer area with some beach vegetation and dunes. And finally, between the blue and the green line, we'll find the actual littoral area with the beach, the sand, people, and this is the actually area where we should find the shoreline. So how to retrieve this different area using satellite images? Well, we can use a classification. We can see here in this example that we can actually retrieve this different area, the backshore, the intermediate, and the littoral area. Another good point of using classification maps is that it's bringing some additional information. we can actually get some contextual information about the ecosystem around the coast and the vulnerability to erosion. For example, if we have some soft cliffs, salt marshes, mud flat, and so on. The problem is that coastal areas are very dynamic, and we need to capture this dynamic if we want a very accurate classification. So in order to capture those different states, we have to use a temporal classification. We're then using multiple images through the year or through a season, depending on the time range we are interested in, to produce a classification. And we can see here that we can actually capture some very interesting dynamic area. So for example, here in this light yellow, we have the tidal area. So this area is sometimes above and below water. So thanks to this temporal classification, we can then build some masks. So here we have the different areas. On the first one, we have the littoral and the intermediate, then just the littoral area, and finally just the sea. Those masks and the boundary line associated will help the position of the shoreline. But we saw that the classification are not just here to help shoreline positioning. It's bringing some contextual information, and they can actually capture some changes. So here we have a classification map for the year 2017 and for 2019. If we get a closer look to a specific area, we can see that in 2070, the sandbar here is disconnected to the land. And in 2019, the sandbar is connected. Let's have a look to the satellite images, and we can see that we have the same situation on top of having more sand in the Wexford estuary. We're going to now pass to the last processor, the Bathymorphoterra model. So what is this Bathymorphoterra model? Is the retrieval of the ocean seabed morphology. So how we can access the seabed? We are using his signature. So we have some sunlight going through the atmosphere and through the water column, reaching the seabed, and then the signal travel all the way back to the satellite sensor. When we're going through the water column, we can see that there is some different suspended particle at the bottom, and it can mask the seabed. Once we have the spectral reflectance, we can then retrieve the depth. For that, we are using a physics-based inversion model. The depth is assigned depending on the reflectance value. So for example, here we have some light yellow linked with some shallow water. So this methodology was developed by Hedling, and the software used to produce this model is IDA for Image Data Analysis. However, using the reflectance information, we have some limitation, and the main one is complex water. So on the left image, near to the beach here, we have a very clear water, and we can see some coastal features, probably rocks. But for the Cork estuary, we can see some sediments which are masking the seabed, and the reflectance obtained for this area here is not the one of the seabed, but is the one of the sediment. So our methodology have 4 steps. The first one is the selection of the image. We saw how sediment can interfere with the retrieval of the seabed signature, but we have similar problem with glint, for example, and cloud cover. So we need a clear image with no glint, ideally, but just few glints to get a proper Bathymorphoterra model. The second step is the atmospherical correction. We need a very reliable correction because we saw that the signal crossed the atmosphere twice, one between the sun and the water column and on the way back to the satellite sensor. So we started a research analysis to compare the impact of the different atmospherical correction on the production of the bathymorphology. So we compare IDA correction here with acolyte and SAN2 core. And the bathymetry obtained after this correction is compared with some in situ bathymetry obtained by our partners. We can see that the resulting bathymetry from IDA is the closest to the in situ one. And we can then say that the atmospherical correction provided by IDA is the best estimation of the reflectance. We use then IDA to produce our bathymetric model. We have here an example of a bathymetry chart for South Wexford. We saw before that the sediments and other suspended particles can have an impact on the reflectance we use to retrieve the depth. So we are going to build some confidence map to evaluate the confidence we can have in the depth information. So the question here is, do we have some suspended particle or sediments, and where are those particles to prevent and to give us the information about where we actually see the bottom and where we actually have the proper depth information. So our confidence map have 3 different levels: good in green, intermediate blue, and bad in red. Those levels are chosen depending on the reflectance information and the water clarity. So first, we're looking at the reflectance. We need some realistic positive value. And then we look at the different concentration of the particle in the water column. In one hand, we have the colored dissolved organic matter, and in other hand, the suspended particle matter. Depending on their concentration, we can evaluate the water clarity and then have a confidence score for our bathymetrical chart. Here we have a quick summary of our results. So for each of our area of interest, we have different bathymetrical model, and sometimes we can see here we even produce for the same dates some extra bathy chart with different atmospherical parameters to test their impact on our classification. Thank you for your attention.